So like Richard said, I'm going to be talking about, what happens after a cancer diagnosis. So talking about, germline genetic studies of mortality, for example. So I think most of us probably don't need much convincing that germline genetic tools are useful for identifying targets for cancer prevention. And so by germline genetic tool, I mean things like Mendelian randomization, genome-wide association studies, and polygenic risk score approaches. And the word germline just refers to the fact that we're talking about inherited genetic information of parents. So, we're talking about to distinguish it from somatic tumor genomics, which is looking at changes within a tumor that aren't inherited. So, these kinds of germline tools have been very successful at identifying causes of cancer incidence and identifying targets for prevention. But there've been very few germline studies of what happens after cancer diagnosis, so survival, mortality, those kinds of things. And in a way, that's kind of unfortunate because in a way, the pathway to translation is kind of more obvious and more direct when you're talking about cancer survival. And the challenges that we face in this space is that we're kind of dealing with small sample sizes, collider bias, treatment-related biases, low heritability. So actually, there's a question mark there because we don't actually have any reliable quantitative estimates of survival heritability, but it's probably fair to say it's lower than for cancer risk, probably quite a bit lower. And then tumor heterogeneity, so especially things like somatic changes that happen within a tumor. And so there's question marks. Can you actually use germline genetic information to proxy an effect that's happening within a tumor that can undergo quite substantial genetic changes? So that's kind of like that's where the ICEP progression and treatment theme comes in. So this is what a theme I co-lead within ICEP. And so the aim of this theme is to conduct germline genetic studies of survival to see if this approach can identify novel treatment strategies, taking into account those challenges and limitations I've just described to you. So, and we've conducted, several studies. I'm going to give you a snapshot of some of those studies now in the next few slides. So the first study I wanted to present today was a genome-wide association study of lung cancer survival. This is actually a meta-analysis of 4 independent studies. So ILCO, the International Lung Cancer Consortium, Genomics England, the Dana-Farber Cancer Institute, and the Michigan Genomics Initiative. And we defined our primary outcome as death from all causes after an early stage lung cancer diagnosis. And we had 5,600 cases and 2,100 deaths. We also had independent studies for replication, and across all studies, we had 14,000 cases and 7,800 deaths. So these are our main results. We found 1 GWAS hit on chromosome 1, RS12062054. And then on the right, you can see our QQ plot. In one sense, the QQ plot looks lovely in the sense that it shows no inflation, which is a good thing, but it also shows that there's no associations across the genome, that basically everything is on the null line, and it's just that 1 GWAS hit at the very end that's kind of perking up. So, and so then this is the association of the GWAS hits stratified by the studies in the meta-analysis, and you can see that basically similar across the studies, no very little heterogeneity, which is a good thing. And then this is, but unfortunately, it didn't replicate in our independent data sets. And but when I showed this to my colleagues in ILCO, they said that they didn't think TCGA was a very reliable replication resource. It doesn't have a very good follow-up data. And in particular, we only saw our GWAS hit in early stage lung cancer survival. It wasn't associated with late stage survival. And TCGA actually does it. This TCGA data set does include a lot of late stage diagnoses. So maybe it's not the ideal replication study. This is the the genomic region where the GWAS hit resides. So it's on chromosome 1 between the CAPN9 and C1orf198 genes, if that means anything. I've not heard of them before. But this region has previously, in previous genome-wide association studies, it has been linked to venous thromboembolism as well as other traits. But this is interesting because VTE, or venous thromboembolism, is the second leading cause of death in cancer patients. So possibly suggesting maybe there's some kind of, if this isn't a false positive, maybe there's a thrombotic mechanism involved. So next, we also looked at the impact of treatment, and we also assessed the proportional hazards assumption. So we adjusted our finding for treatment so that we expected quite a lot of work trying to harmonize treatments across the different studies. It's quite a tricky space because there's so many different cancer treatments, but eventually we came up with a scheme, and the main takeaway message from this is that we saw really no impact of treatment on our association. So if you can see, the very top panel is are the effects without adjustment for treatment stratified on tumor stage, and essentially the results don't change. So as you go down the plot, those are different treatment adjustments, and we didn't really see any impact of treatments. Then this is just looking at the proportional hazards assumptions. So I'll just go through that. So the main thing here, so this is an ILCO. So this is just looking at survival curves stratified on genotype for our GWAS hit. And essentially, the survival curves are basically pretty much parallel in both genotype groups. So that suggests no violate, or it's consistent with our proportional hazards assumption. And then I mentioned collider bias at the very beginning. So this is a bias that results, because we're conducting the analysis within cases, this can introduce a selection bias, but only if the thing you're looking at is also a cause of cancer risk that can result in this bias. So what we did is we looked to see if our GWAS hit is associated with risk of lung cancer, and we found an odds ratio of 1.01, quite a precise, reasonably precise confidence interval, suggesting no association with cancer risk. So we concluded that the risk of collider bias was quite low for this variant. Then we've also conducted some PD-1 positive control analyses. So many of you probably are aware that PD-1 is a target of immune checkpoint inhibitors, and this is an approved treatment for lung cancer. So inhibition of this protein pharmaceutically reduces mortality in lung cancer. So we reasoned that germline genetic lowering of this protein is a natural mimic of pharmaceutical inhibition. And we found that, as expected, this figure shows that indeed germline reduced PD-1 protein levels is associated with reduced risk of mortality in all tumors combined, early stage lung cancer, and possibly late stage as well, but that was more uncertain. But this is similar to what we see with pharmaceutical inhibition. Also, we're very concerned about statistical power. So what we did was we took the lead variant for PD-1, the cis variant for the PD-1 protein, and using the observed hazard ratios, we did some power calculations to see how many samples would we need to discover PD-1 in a hypothesis-free framework at an alpha of 5 times 10 to the minus 8. That's the conventional threshold for statistical significance in GWAS. And we found that for early stage lung cancer, we would need 79,000 cases. For all tumors, we would need 200,000. And for late stage lung cancer, we would need 700,000 cases. So these are kind of really mind-boggling numbers. And we're very far away from that kind of number. So we're probably very underpowered for these kinds of variants. So that would be common variants, well, kind of small effect. So just to sum up, we found one variant associated with survival, but didn't replicate, possibly a thrombotic mechanism. Germline genetic lowering of PD-1 mimics pharmaceutical inhibition of PD-1. Little to no impact of treatment or collider bias, no violations of the proportional hazards assumption, but we are probably very underpowered. And so in terms of future directions, given I think to really make progress in this area, we need kind of fundamentally different approaches to make headway. So, for example, using less traditional study design. So instead of prospective cohort studies, maybe relying more on clinical settings to kind of get the sample numbers we need. So, for example, in the NHS, in the Genomic Medicine Service, more than 7,000 lung cancer cases receive tumor panel sequencing every year. And so you might recall from a slide earlier that the total number of cases we had in our meta-analysis were 14,000 cases. And that reflects years of hard work to get that kind of number. But in the NHS, they're sequencing 14,000 cases every 2 years. So, and it turns out that there's been some recent work to show that you can actually impute genome-wide germline genotypes from the off-target reads of tumor panel sequencing. And that this figure at the bottom just tries to illustrate that. But so at the moment, so what I'm doing now is I'm in discussion with the Southwest Genomic Medicine Service to see if we can try to implement this approach in the data that they have to assess feasibility of this approach. But that could be, I think, a future direction. So,
probably, I think you've given a really nice illustration of what I'm doing. So I suspect it'd be better to stop. Yeah. Okay.
Yeah, that's
sorry about that.
Yeah,
but I think, I mean, what you gave us was absolutely fascinating, and that link to the NHS Genomic Medicine Service is really, really interesting. Yeah. Any questions from that? Anna.
When you're separating,
oh, so it's basically all non-small cell lung cancer. We don't, and with the difference with so it's any non-small cell lung cancer, and the kind of the median survival times they vary between say 2 and 3 years. ILCO, they kind of censor everyone at 5 years. Follow-up was a bit longer in the other studies, but we're going to repeat the analysis censoring it at 5 years of follow-up. And yeah, does that answer your question?
That was, you said the survival was taken 5 years. I thought that's really low. I'm not to know, 20%. Hardly anybody survives.
Yeah, I mean, some people do, but yeah, you're right. The vast majority. Yeah.
Thank you. There was another question I saw from that side. Was it Matter? But yeah.
I haven't thought this through, but is there any? I get a sense of how much survival, cancer survival, how heritable it is.
Yeah.
In its own right. I mean, if you can look at chip heritability, I mean, lung cancer is special because the survival rates are so poor.
Yeah.
But do you have any sense of how much the sort of germline genetics influence cancer survival?
So I mean, only in the sense that I think it is probably a lot lower than for lung cancer incidence. It's probably higher in early stage lung cancer than late stage lung cancer, and that's one of the reasons why we decided to make early stage lung cancer our primary outcome, because you can. I think the heritability of survival after a late stage diagnosis is probably really close to zero, because but so if the heritability is probably most heritable the earlier the diagnosis. I think ILCO did try to do some heritability analyses, and it was kind of like single digits, but they didn't really use the most appropriate method. And so one of the things we want to do is we want to use some newly developed methods for heritability in a survival context to try and better quantify that.
I mean, lung cancer is particularly challenging because survival rates are so low. But hopefully it will change in years to come, particularly in the UK, which is so widespread screening. We will have much more many more cases diagnosed at an early stage.
Yeah. Fantastic stuff. Thanks so much for that. Cheers.